All right. Let me
Thank
share
you.
my screen. Yeah, sure. So is my screen visible?
Yes, the screen is visible.
Okay. So this is going to be like a hands-on session, but I want to like talk a little bit about quantum teleportation, like the theory behind what we're doing, and some more basically. Okay, the theme of this is going to be entanglement for quantum communication protocols. Um, there are several quantum communication protocols which try to leverage, entanglement for doing some kind of new thing in quantum communication. Um when you look at quantum computing, or just what is the point of doing something with something which has something from quantum in it versus just using classical. It's because you get some sort of advantage, or mainly you're able to do something you're not able to do purely with classical things. And one of the key resources for not just quantum communication, if you look at things like applications like quantum sensing, and things which aside from quantum computing, which you accomplish, where you're trying to implement quantum technologies. um, One of the key resources for being able to do that, which is from the intrinsic nature of quantum systems, is something called as quantum correlations. So quantum correlations are, properties of quantum systems. They're core properties of quantum systems, and things which you cannot, measure classically, purely classically. So if you take a plain classical system and a system which has some non-classical or quantum nature in it, what is the difference between the two? The system with non-classical, nature probably has some non-classical correlations in it, specifically quantum correlations. Now, entanglement is the one which everybody knows about, right? And with that, part of the reason is because we are able to accomplish these kind of things by leveraging entanglement. But it is not the only quantum correlation. You have correlations such as quantum discord. You have things like contextuality, and there are several measures which people have come up with, and there are not even like concrete sort of mathematical expressions you can write for several of them. Some of them you can come up with expressions, but for some of them you don't even have a way to properly analytically define the form they will take in terms of some kind of equation, right? But these quantum correlations form the key resources in quantum systems, which can be leveraged in order to do something that you cannot do purely classically. And today we are just going to talk about, entanglement, which is extremely important for several, quantum communication protocols. And the most majorly known one, you have teleportation. You also have things like CHSH games and so dense coding, etc. But in today's, like right now, today, I'm just going to talk about quantum teleportation, but also some supplementary concepts in quantum computing which are essential for being able to implement it from start to end. So if you understand quantum teleportation as some kind of, it's just a set of steps which you write in Qiskit, of course that is there. But you have other topics like, quantum state tomography, which is an essential part of quantum technologies. So we will be discussing these things one by one, right? I see some question in the chat. Let's just take a second to. Oh, sorry, just a second. Okay, I need to. For some reason, I'm not able to maximize my panel. Let me just stop sharing for a second. Okay, the question is post-quantum cryptography is working on other than factorization and discrete logarithm problem. What are those for pre-QC? Well, that depends on, so as I mentioned, right? So um, the difficulty of, okay, let's come back to the question later. I don't want to change the, we were talking about the, we are starting the new lecture, so maybe I'll take any remaining questions at the end. Okay, I hope my screen is visible. Is my screen visible? I think not. Yeah, I think it's visible now. So we'll resume. So first for this notebook, we have Qiskit 2.0.2. Then I have Qiskit Air and Qiskit IBM Runtime. But I also have Matplotlib and PyLatex ENC. This is a 3.12 Python virtual environment. But you can, but I've installed Matplotlib and PyLatex ENC, but you can probably also just install Qiskit visualization and things would work. But if you're getting some kind of error related to Matplotlib, if you install Matplotlib and PyLatex ENC and like restart your kernel, restart your this thing, it will work. Okay, so I have already installed these packages in my virtual environment, but I'll clear all outputs so that we can start from the beginning. All right, so to start with for introduction, so we know that the priority, one of the biggest priorities of like doing quantum computing is to tackle utility scale problems. And the reason for this is that if you are not doing quantum computing at say some 100 plus qubits, it's not a strict 100, the number 100 is not a strict number, but you need to at least be thinking of using around 60 to 70 qubits, because anything less than that you can accomplish on a classical computer. And why would you need to use a classical computer for something that you can solve? If you can solve something with a classical computer, why do you want to use a quantum computer, right? Classical computers are pretty cheap and they're pretty accessible. So the so as I said, one of the biggest priorities of doing quantum computing today is to tackle utility scale problems for which you need at least say 70 to 100 qubits. And but for doing this, we will need to move information around on a quantum computer from one qubit to another. So if you have a device that has 133 or 156 qubits, then not every qubit is going to be connected to another qubit. So you will come up with scenarios where you have to move information from one qubit to another distant qubit. So there are well-known protocols for doing this, but some of the most foundational were cast in the context of sending information between distant parties. So generally, when we talk about quantum teleportation protocols and the like, we talk about Alice and Bob, but sometimes Alice and Bob could be, qubit 1 on a quantum computer and qubit 156. Now, I'm just using these numbers loosely, but I hope you get a sense of what I'm trying to say rather than like the literal meaning. So throughout this particular, talk, we will use sometimes, use language like, distant friends sending information, Alice and Bob. Okay, another thing is quantum teleportation is not the sci-fi thing which we saw, which we can see in movies like, Avengers or recently Fantastic Four. That's not that's not the quantum teleportation that we are talking about today. Quantum teleportation is something pretty, it's something that is tangibly possible, but it is in the context of sending information to one place from one place to another. It's not the sci-fi context of, you're shooting something with a ray and it goes from this place to place A to place B. It's not that, but it's more about the flow of information from one place to another, right? So in this sort of talk, we will discuss quantum teleportation, which is a key quantum communication protocol that uses entanglement to transfer an unknown quantum state from a sender, which is Alice, to a receiver, whom we'll call Bob, without physically moving the particle itself. So this is accomplished using a shared entangled state, which is sometimes called as an E-bit, which stands for an EPR bit, EPR or an EPR pair. And this is used to send an unknown quantum state to a distant friend, requiring supplemental classical communication. So the setup for doing this to perform teleportation is that Alice and Bob must first share an entangled quantum state, which again, as I mentioned, we can call as an E bit, but it's specifically an EPR sort of bit. And Alice has the Q bit. She wants to send Q. Okay, Alice has some, wants to send some quantum. She wants to send a quantum state Q from the qubit she has, and she performs a joint measurement on her two qubits. So the one she wants to send and her half of the entangled pair. So the process, I've written qubit here, but it's more like quantum state, right? So the process itself would be that Alice's measurement will collapse the states of her qubits and produce two classical bits of information. So she will send these two classical bits to Bob, and based on the two bits he receives, Bob will perform a specific operation on his half of the entangled pair. And the result of this operation is that the operation Bob performs transforms his qubit into an exact copy of the original qubit Q. Now it's we say exact copy, but it's more like what to say. You want to sort of transfer the quantum state from Alice to Bob. Now, the original qubit in Alice's position has been destroyed in the process, which is consistent with the no cloning theorem. So the principle where you say that an unknown quantum state cannot be perfectly copied. And the way we are accomplishing this is by consuming the entanglement or like burning entanglement to enable this transfer of quantum information. So now what is entanglement? So entanglement is a phenomenon in quantum mechanics where two or more particles become linked in such a way that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by large distances. So this means that a measurement on one particle instantaneously influences the state of the other, which so like what we mean here is that so if I have so two points here. Entanglement, so if you mathematically want to see what entanglement looks like, it is basically not being able to write basically separate the way you can represent states on different qubits. For example, on a quantum computer, if you're representing the quantum state, you cannot separate them with a tensor product. Okay, that sort of signifies the existence to some extent of entanglement in the system. And secondly, and this is possible even if you're talking about adjacent qubits or like really distant qubits. So the distance or the physical distance does not matter in this context. So, and in cases like if you remember all the Bell state creation and Bell state and these kind of things, you can sort of understand that measurement on like when you have a uniform like superposition. Say if you have something like 0 0 and 1 1 on say for example you have a 2-qubit system and you have created a Bell state 0 0 plus 1 1 1 by 2 1 by 2 times 0 0 plus 1 by root 2 times 0 0 plus 1 1, right? So this means so if I measure any one of if I say I'm just measuring one qubit, right? I know that if I measure one qubit and it says 0, then the other qubit is also 0 for sure. And similarly, if I measure one on one qubit, then I know that the other qubit is also at the state 1. And in some sense, the reason this is possible is because of the presence of entanglement. And this means and in this case, a measurement on one particle instantaneously influencing the state of the other. This is something which is called a spooky action at a distance. And this is a unique and powerful correlation, which is the fundamental resource underpinning many quantum communication protocols. So here when we talk about an unknown quantum state, we can just represent it as any general quantum state psi is equal to alpha 0 plus beta 1, right? Where mod alpha square plus mod beta square is equal to 1. and alpha and beta are complex numbers. So any general quantum state can be represented as cos theta by 2 0 plus e to the I phi sin theta by 2 1. So now here, so we need to, if you want to transfer information from present in any any random quantum state, you need to first understand what a random quantum state looks like. So here normally we usually talk in terms of alpha beta, but parameterizing this in terms of theta and phi has its own benefits, and we will see why in the upcoming, like in a few minutes, right? So if you remember the block sphere notation, we will, again see the block spheres coming up in a few minutes. But if you represent any quantum state in the block sphere, any random state, then, with here mathematically we represent any random state as alpha 0 plus beta 1. But if you represent it in the block sphere itself, how do I move a random state from one place to another? I can do that if now forget about any sort of quantum state. If I have a sphere and I want to move from one point to another point in the sphere, how can I accomplish that? I can accomplish that by moving around in the three possible directions, which is, the x-axis, the y-axis, and z-axis. If as long as I rotate along the x, y, and z axis, I can, I can reach any general state. So with that in mind, now we have, we have gates which can accomplish similar things in quantum computing as well. So now if you come back to a block sphere, if you want to move from any random state to another random state, you can perform Rx, Ry, Rz rotations, and you will be able to reach any random place. But before that, let us understand the concept of density matrices. So any quantum state which is represented as psi can also be represented via its density matrix, and this form is useful for denoting a probabilistic mixture of pure quantum states. And in the case of a single qubit, the most general form would look like, so you have outer product of psi with psi, and this is the density matrix rho, which is nothing but, you have the cos theta by 2 and e to the I phi sin theta by 2. Now, if you compute the density matrix, this is what it's going to look like. And if you want to actually write this in terms of the polys, you have rho is equal to 1 by 2 times identity plus sin theta cos phi x plus sin theta sin phi y plus cos theta z. Or in general, you can write any rho as rho equal to 1 by 2 times identity plus rx times x plus ry times y plus rz times z. Here, what are these x, y, and z? These are the poly matrices, poly x, poly y, and poly z. So, where rx plus ry plus rz, rx square plus ry square plus rz square is equal to 1. So, if you want to actually now represent it in the block sphere, you have r is equal to rx, ry, rz. Now, let us make an arbitrary quantum state using random numbers. So just to mention the Qiskit version, I'm using 2.0.2. And the rest, and I'll also tell you the Qiskit IGN runtime and air versions. So Qiskit IBM runtime I'm using is 0.41.1. Can use slower versions as well, I guess, but it's always best to use the most up-to-date version. And Qiskit Air is 0.17.1. So now I'm importing NumPy and setting a seed so that we are able to repeat this again and again if we want, and have the same states. So now here I'm just coming up with a random value for theta and a random value for phi. So you can just print it also here. So as you can see, the theta I have is 1.3.1 and my VR phi is 4.525 something. So now if I want to get the R vector, basically the Rx, Ry, Rz, this will be this is related to the corresponding representation on the block sphere as well. So I can write a function for that based on what we discussed here. So yeah, so this is basically what's being done. You have Rx is equal to np dot sine theta times np dot cos Vr phi, etc. Then you can get the R vector. And we will just print this here. So we have theta is this, the same thing. I'm just printing it again. And Rx, Ry, Rz corresponding to this is basically minus 0.17 minus 0.949 and 0.257. This is Rx, this is Ry, this is Rz. And this can be plotted on a block sphere. So this is where this random state is staying. Now, we also need to understand a technique called as quantum state tomography, which is necessary. So if you only measure the quantum state in the computational basis, which is in 0 and 1, the phase information, which is like related to the complex numbers, this will be lost. But if we have many copies of psi, then by repeating the preparation process, we cannot clone states, but we can repeat the preparation process. We can estimate the value of Rx, Ry, and Rz by performing quantum state tomography for the density matrix rho, right? So you have a density matrix rho, which is of the form half I plus Rxx plus Ryy plus Rzz. It holds that the trace of x times rho gives you Rx, the trace of y times rho gives you Ry, and the trace of z times rho gives you Rz. In the case of Rz, you have trace of z rho equal to, this is basically just the mathematics describing how you get it. But yeah, so you can basically get what the RZ value is by subtracting the probability of mod beta square from mod alpha square. So since this is the easiest, we can start by so now we have prepared a random state, right? We technically know what Rx, Ry, and Rz are. But this is just an arbitrary random state. So now if we want to find out what is the RZ value corresponding to this random state, say I'm given a random state and I want to find what is the Rx, Ry, and Rz. Now, how can I do that? You can start by first estimating the RZ value, and to do that, you can create we can create a quantum state and measure it. And then we can, repeat the preparation and measurement many times. We use the statistics of measurement to estimate probabilities above and thus estimate RZ. So we already did that, right? We already used theta Vr phi and we were able to produce this random quantum state. So let us do that again and actually do a measurement as well and draw a circuit which prepares that, right? So this is the circuit. Now, using air simulator, we will measure it in the computational basis to estimate RZ. So if I want to actually find out what is the RZ corresponding to this random state, I need to basically do this in order to figure it out. So this is just the implementation of this particular circuit. So you need to import Qiskit Air you need to import air simulator from Qiskit Air, and then you need the generate preset pass manager to transpile your circuit before running. Then you have you can use the sampler from Qiskit IBM runtime, but I'm using the backend as the air simulator. Then I will plot the histogram then I'll plot histogram using the Qiskit visualization. So to start with, we are defining the backend as air simulator. Then we are using 1000 shots. You can use how many ever you want. Then you basically transpile the circuit. Then you run it on the sampler using mode equal to backend. And then you get the counts you can get the counts from the results data. And then here we plot the histogram counts. So as you can see here, you have 0 being coming for 647 out of 1000 shots, and 353 times you have the state 1, which is coming up. So approximately, if I want to understand RZ, how do I calculate it? It's counts of 0 minus counts of 1. divided by number of shots, which is 1000. So let us compute that, and we also already know the exact value of RZ, so we can compare it with that, right? So if you see here, the exact value of RZ is 0.2577, and approximately you are measuring it as 0.294. Now here I've used 1000 shots, right? Say for example, I increase it and I use 10,000. Let's see what's happening. Now, if you see, if I increase the number of shots to 10,000, you see that it's kind of getting closer, right? This is because ideally at infinite number of shots only you can reproduce the exact, if you want to understand exactly what will be the counts, it's going to like the more number of shots you do, the better you will be able to represent the probability distribution that it really emulates. So say I only use 10 shots, right? I will have a very terrible result, but I want to demonstrate this. So, okay, it's not that terrible. It's still 0.2, which means it's reasonable and that the mathematics is very robust. But you need to use like a minimum number of shots so for 1000 we are getting, okay, in this case we got 0.252, which is pretty close. But you have to use, in general, it's better to use a higher number of shots. But for simple experiments, if you're using, say, 1 lakh or 1 billion shots, it's a waste of resources to repeat the experiments that many number of times. I saw a question as to why n shots. This is because you never try to judge the state or the actual an actual quantum state by doing one measurement, right? You, from a quantum computer, if you want to extract information about what quantum state it exists in, you have to do some sampling. And by doing this sampling for a specific number of shots, you will kind of be able to emulate the probability distribution of what all shots have come, and from that you kind of backtrack and understand what state it existed in. The only problem is here we have only 1 qubit, right? So it's pretty doable. For even maybe 10 qubits it's doable, but at 10 qubits you will not have two states. You will have 2 to the power 10 states, which is 1 to 1024. So think about using 50 qubits, right? So if you're sampling in a 50 qubit system, you'll have 2 to the power 50 possible states. So the n shots is a very important parameter which needs to be like very finely and specifically controlled, such that you're not using too less, but you're not also using unnecessarily too high number. So, right. So now we have now here of all possibility states for finding expect results. I didn't understand that question. Maybe you can rephrase that and we'll come back to it. But yeah, so now we find like the RZZ approx which we calculated is not very bad. I mean, it's kind of pretty close to the RZZ which we started with, right? So now using this quantum state tomography method, we have estimated the RZ value. And in this case, since we chose a parameter for the random state, we know the value of RZ and we can check our work. But by its very nature, utility scale work is not so trivial to check. So yeah, as I said, okay, I can actually demonstrate it to you in, let's just say QC is equal to, using QC here. Yes, I don't, okay. Let's call this QC1. Let's say quantum circuit of n, and I will define n here to be 2 first. And then I'm just using, yeah, Hadamard is probably the best because let's do it like this. For n for range n, use QC1 dot h of n, QC1 dot, I'll just use QC1 dot measure all. Okay. I can use the same pass manager, so I'm just going to call this ISA QC1 equal to can say I say QC1 equal to PM dot run of QC1. Maybe I'll drag this up. Okay. PM dot run of QC1, and then use the sampler. I'm just gonna copy this because it's easier. And call this job 1 so that we don't rewrite any of those. Okay. Should also be counts 1. This should be n minus 1. I'm not sure what's happening here. Okay, counts is equal to. Let's first break here and let us first. Okay, sorry about that. Let us first draw the circuit and see what it looks like. Okay, so this is the problem. So no, it's not possible. That is what I wanted to demonstrate here actually. So this is the mistake I made. It should be n minus 1. No, it should be n only. Yeah, so this is the thing we want to have. This is the kind of circuit I want to have. So basically I'm implementing a Hadamard on all qubits so that I get a uniform superposition of all states. So now if I actually measure and sample here, I will be able to. Okay, I need to do this step by step. Probably I need to redefine the pass manager. Let's just get this part as well. Okay. Let us print the result. So we see that it's a primitive result. To see if MEAS works. So now we have, okay, so MEAS worked. And as you can see here, so now I have 0, 0, 0, 1, 1, 0, and 1, 1. So now I put n equal to, so I put n equal to 2 and you see that there are 4 states, right? So this is 2 to the power 4. And now if I put 3, and if you see like, okay, the number of shots is 239. So I had 1000 shots and that is split between how many states? 4 states. So I have around 239, 237, 266 and 258. And ideally, this is right because ideally I should have, equal counts for each state. But since it's not a perfect scenario, that's not happening here, right? But say, for example, that I want to go to 3. Now you see that this number of shots has been split further and you have counts. This is these are 8 states. So for n equal to 3, you have 2 to the power 3 states, which is equal to 8, right? So now say I'm going in, forget 3, I'm going to go to 8 directly. So now what happens here? So now if you see, you have, the number of counts for each sort of state to be split between 2 to the power 8 different states, which is what, 512? No, it's 256, I think. Yeah, it's 256. So here you have 256 states, and that's why it's all overlapping. And you see there are not sufficient, so because this is an ideal circuit, you know that each state should be counted an equal number of times, right? But that's not that is not sort of what is going on here. So now I have to increase the shots to say 100,000, and now let's see what happens. Now, if you see, it's looking all more or less similar, right? So, and this is more close to the ideal state than what we just saw. And that is why this n shots parameter is different. Depending on the sample size of the sort of system depending on the size of the system you're sampling, you have to give an appropriately, scaled n shots. Otherwise, you will get a rubbish result. So, and I think I have, we have seen this demonstrated sufficiently here, because as I said, when you use 1,000 shots, what was the result like? This is not the state that we are trying to form, right? This is a Hadamard on all qubits, so it should be equal superposition with each state actually measuring to the same probability. But when the same thing, when you use 100,000 shots, which is more appropriately scaled, you see that this is a much more reasonable result. And this will stand as this is just for 8 qubits. Mind you, it's not even like over 10. This is simply just for 8 qubits. So the point is not that okay, it depends if it depends on whether the aim of your algorithm is to actually have every single state in the superposition produced, or just some high probability state, right? So if you're just measuring a high probability state, then 1024 shots might very well suffice. But there are two takeaways from here. One is that if you want to sample all the states in a okay, this is called as a basis. Okay, so all the states which are coming here, this is the basis of a particular quantum system in some sense. So the basis will consist of all possible states which can come as an outcome of your sampling. So if you want to move closer to the ideal distribution of sampling over the entire basis, ideally you need to use infinite shots. Okay, but practically that's not necessary, and it's also not feasible to implement 1,000 shots. You can implement a very high number of shots, but infinite is obviously not possible. But you will move closer to the ideal result by doing that. So yeah, that is, I think I combined both the points. So I think that is both that, that's the point that I wanted to convey. I hope that answered your question, right? The why the n short sort of parameter is significant. But anyway, coming back to quantum state tomography, we still have quite a bit left. But estimating the Rx value and the Ry value, we have kind of so there is a theoretical explanation for how you can do that, right? So based on that, we will do the tomography protocol, and we can figure out what is Rx and Ry. Now, we already know Rx and Ry since we came up with the random, state. However, we want to know how we can do this tomography, like what is the process of doing it in order to do it on a genuinely random state, right? So again, we create the same state, and here in this case, we have implemented a Hadamard. So here we have implemented a Hadamard, and the Rx value is basically the counts of 0 minus counts of 1. There is also one more thing here, but I mean, I think I will come back to it later if necessary. But here again, because I've implemented the Hadamard, it's basically effectively measuring in the X basis in some sense. So now I can do the same counts of 0 minus counts of 1 to actually estimate Rx. So now here we see we went from minus 0.179, and here it's minus 0.19, which is approximately equal. Now maybe it's not an exact match, but again, approximately it's an equal It's an equal sort of measure. Then if I want to estimate Ry value, similarly, we can do the state tomography for Ry as well. And in this case, we have to implement an S-dagger operator before and then a Hadamard before measuring in order to do everything in the Y basis. So now in this case, our So again, we have Ry is approximately minus 0.94, and here you have minus 0.94 as well. So now we have estimated all components of the R vector, and we can write the whole thing. So the estimated vector is minus 0.19, minus 0.9442, 0.252, and the actual one is this, and it's pretty close, right? So we have obtained it fairly accurately using the state tomography method. Now we come to quantum teleportation. Let us consider the situation where a character Alice, let's say qubit 1, she wants to send an unknown quantum state psi to her friend Bob, who is far away. Say on the other end of the quantum computer, we have another qubit. Assume they can only communicate with classical communication like using email or phone. Alice cannot copy the quantum state due to the no cloning theorem. If she repeated the same preparation process many times, she could build up statistics, basically what is Rx, what is Ry, etc., right? But what if there is only a single unknown state? This might have emerged from a physical process you want to study, right? So here we kind of came up with an arbitrary Rx, Ry, Rz, and then we keep repeatedly preparing it to figure out something. But in practicality, it's not that every single time you will get a state which can be reproducible again and again, right? So what can be done in these kind of cases? It could also be part of a larger quantum computation. So in that case, how can Alice send this state to Bob? So now she can do this if she and Bob share a valuable quantum resource called as a shared entangled state. Like the Bell state, which was introduced earlier in previous lessons. So it's basically 0, 0 plus 1, 1 by root 2. And you might sometimes also see this referred to as an EPR pair or an E-bit, which is a fundamental unit of entanglement. So if Alice shares such an entangled state with Bob, then she can teleport the unknown quantum state to Bob by performing a series of quantum operations and sending him two bits of classical information. So what is the actual protocol? Now we start with the assumption that Alice has an unknown quantum state psi to be sent to Bob. Alice and Bob share a 2-qubit entangled state or an E-bit, each having one of the qubits physically at their location. So what is the actual procedure? So this is the actual, this is the way you do it. So Alice will start by entangling psi with her part of the E-bit using the CNOT gate. Then Alice applies a Hadamard gate to psi and measure both her qubits in the computational basis. Alice sends Bob her measurement results, which is either 0, 0, 0, 1, 1, 0, or 1, 1. And then Alice performs a correction operator based on Alice's 2-bit of information on his part on the E-bit pair. So if it's 0, 0, then Bob does nothing. If it's 0, 1, Bob applies the X gate. If it's 1, 0, then Bob has to apply the Z gate. If it's 1, 1, then Bob applies IY equal to ZX gate, right? So you can find more details of what this is if you look at this particular reference. It's there in the notebook, so you can look at it later on. But now let us actually look at the implementation of how this works, right? So now, okay, from Qiskit, we need to import quantum circuit and NumPy, and we need NumPy as well. So we import that as NP. Then you have QC equal to quantum circuit of 3, 3. Yeah, so this is just a blank quantum circuit which we have started. So now we need, let it be that Alice has an unknown quantum state psi. So we will create this using the U gate which was used previously, but this is just for a reference and verification. You can use any randomly generated state as well, and this should work, right? So you have created this random unknown state psi here, which we actually know, but Alice doesn't. So we have that here. And we can visualize this basically using Qiskit visualization. So 1 and 2 qubits have nothing going on, so they're at the 0 state. But at the 0 state, at the 0th qubit, which belongs to Alice, you have the random state, which we kind of created using this circuit, right? Now, before this protocol begins, we have to assume that Alice and Bob have a shared entangled pair, right? So I mean, here, ideally, you should start by creating the entangled pair, but it's okay here. You can do do it in either order because we are just doing it for demonstration purposes, right? Yeah, so now we we create an entangled pair between Alice and Bob. So 1 and 2 are like Alice and Bob. So yeah, you have you put a Hadamard and then you put a C0 gate, and then you have created basically this is the basis of like creating a belt state. So you have this. Now next Alice needs to entangle her part of the share, like entangle psi with her part of the shared E bit. So this Q1 Q2 pair together is the shared E bit because this is where the bell state exists, right? So now what Alice needs to do is entangle, say 1 belongs to her, right? She needs to entangle this U with this with Q1. And how can she do that? She can do that by implementing a C0 gate and then another Hadamard. So the reason you're putting barriers here is to make sure that, you know, during compilation, these things don't get cancelled out, like one doesn't cancel out the other. So yeah, that's why we have the barrier here. Then now we measure both the qubits. So as we know, Alice sends Bob her measurement results as either 0001, 10, or 11, and Bob performs a correction operator based on Alice's two bits of information on his part of the shared E bit. Then this becomes Bob's psi. So basically, after measuring he will implement like, you know, these particular gates as mentioned in these steps. So now this is technically completed the quantum teleportation circuit. So now what should have happened if basically our aim is to move this particular piece of, you know, this random state from here to here, because this is with Alice and she prepared the state. Now the state which was with her has to go from here to here. So now that we have created this circuit, what happens? Oh, something went wrong, I think. Oh, okay, I should have. Oh, we are using the same QC and I ran some cell twice. So let me just run this thing from the beginning. I need to create the empty quantum circuit again. Okay, now. Okay, I'm not sure about this, but then you see that the state which we randomly created here, which was here, has come here, right? So this was the aim of the teleportation protocol, and this has successfully been implemented. So yeah, yeah, I mean, okay, I think it is expected that this can change states, but the main point is that the state which was here should come here. Now, one thing we can do to verify is actually create, let us create another QC, or okay, I'll copy all of this into one cell. No, okay. I mean, I will leave this to you guys as an exercise because you can remove, if you remove the NP dot, the seed which we set in the beginning, you will be able to generate different random state. Basically, this psi which was in the beginning, this would be in different places, of course. So you can test this out. So I will leave that as an exercise. But you can see that whatever state we created initially at 0 has been transferred to qubit 2, which is called Bob's qubit. Now, now one way we can definitely execute and confirm this result is whether to understand whether Bob really has this qubit is to apply U inverse, right? So we know what this U is, which is that this is basically U of theta, VR phi, and 0.0 and 0, right? So if we implement the inverse of that, then we should be coming back to, we should like come back to the basic state once again. So let us implement that and check. Now here I would expect it goes back to the original sort of uniform superposition, and that's what has happened here. So we are back to all states at uniform superposition as if nothing happened, right? So yeah, this is like sort of indicating that the teleportation protocol has worked properly. So the key takeaways here, now I skip part of the theory because again, like you see, it involves a lot of mathematics, and it would probably better to sort of read it from somewhere and understand rather than having me just read out of like the screen. But like if when you're implementing this protocol, these are the things that you sort of have to keep in mind, that like the main sort of thing to understand is why Bob, depending on what information Bob is getting, he does different things, right? So this is different, this is important mathematics to understand, and I would recommend that everybody go back and kind of look into why that is the case. So the key, so for like in terms of takeaways, we can transport a quantum state to a different friend by sharing a pair of entangled bits, with qubits, which we call an e-bit, but it's specifically an EPR pair, right? So does quantum teleportation break the no cloning theorem, which forbids copying of a quantum state? Absolutely not, because the original quantum state given to Alice on one of her qubits was lost in this measurement, right? So it collapsed to a 0 or 1. So this means that the no cloning theorem has not been sort of violated or anything. So in summary, and we have implemented this protocol for teleportation. So although this basically has applications in several areas, one of which could be that, if you want to say move a quantum state from one qubit to another distant qubit or something, that can be done. But mainly this is to like this protocol kind of, it represents or it depicts how quantum information moves around in a system when you do different operations on it. And being able to follow this sort of movement of information allows us to understand it better, to capture or to reproduce it better, and leverage it for applications. So so in this case we have used the entanglement to move information from one place to another. And although we cannot copy quantum states, we can teleport unknown quantum states by having shared entanglement via quantum teleportation. So yeah, we are exactly at around the time to stop. So I'll take any questions. Yeah, I see one question, entanglement pair. So entanglement pair here, we refer to the 00 plus 11 state, which was created using a Bell circuit. This is because when you have 00 and 11, say I'm only measuring one qubit, right? I know that this is the circuit I've implemented. Say I measure one of the qubits. I can for sure tell what would be the state in the other qubit. So that is sort of the special entanglement in this particular state. You can also look into what are G head Z states and what are W states. So those are also states with interesting properties. So yeah, you can look into that.
All right. So basically, we have come to the end of the session. There is one question, probably, if you want to take.
I see one more. Can we share multiple EPR pairs where each EPR pair involves a distinct quantum state? So this is, it's not particularly a complicated question, but specifically a protocol, when you're implementing a protocol, you need to move sequentially. Otherwise, you could disrupt the way entanglement is working in the system. Even though, like if you look at the 3-qubit system, you can also think about subsystems in this one overall system where you have 0 1 interacting some way, 1 2 interacting some way, and 0 and 2 interacting some way. So there is a level of separation. So so if you want to say transport multiple different states, you have to do it sequentially or carefully. If you mix it up, you should make sure that you're not disturbing the correlations and the way they work, right? So I would say it is possible theoretically, but you have to kind of be careful and make sure you're implementing it effectively. Is the circuit run with sufficient sorts to sample all possible states? Yeah, in terms of, yeah, you also need it for statistical correctness. That is right too. Yeah, that is right. But but the most accurate result you want in terms of statistics would be at, as I mentioned, infinite shots, which is not practically possible, and it's also not efficient or needed to use that many. You have to sort of judge how many you need for a particular system. So yeah.
All right, so that's basically, there is one more question, which is somebody
Sure, I
asking
can.
for that.
You can just look it up on Google Scholar, like look for open source, not open source, like look for, look for the papers which are available on archive, so you can kind of read it, like without the hassle of any paywall. So yeah, you can look up any of the. So okay, one note I want to mention. I saw a previous question also. You mentioned, can you provide any reference on a quantum encryption algorithm? And one more previous question is what about the post-quantum algorithms? Can we run these on qubits? I would like to repeat once again that these, protocols, these are purely classical. These algorithms are not quantum at all. However, these are algorithms which cannot be broken by quantum computers. If you look at RSA and ECC, there is a chance that you can break these algorithms by running, like by doing some classical processing, extracting some numbers, and then running Shor's on it, which is a quantum algorithm. You can get some information with which you can break this encryption method. But with quantum safe algorithms or quantum safe encryption protocols, which are purely classical, these are more robust against quantum computers because they're difficult to solve using quantum computers. Even forget classical, they're also difficult to solve using quantum computers. So that is the sort of crux. And there's one more question. Okay, there are two more questions. PQC is working on other than I mean, so post-quantum cryptography is so post-quantum cryptography is not a technique, right? It is more of a framework which is developed to be more robust against quantum computing. So I would say that you think about the question in this context. And then the next question, ma'am, does simulator still work? Okay, so it depends on, so you need to import air simulator from Qiskit_air rather than Qiskit. So sometimes it's not going to work because the air simulator, the whole of air simulator formalism has been moved to Qiskit air. So if you import air simulator from Qiskit_air, it's a separate package which you need to install, and it is community maintained. Oh no, sorry, it's not. I'm sorry about that. I'm sorry, it's not. But you need to install that package separately and then you can use it. So yeah. Can I provide any reference book on quantum communication? Sure, I will think about it and get back on that. And like maybe also the paper, I can try to come up with it. But I would mention, just look up things in like Google Scholar. You will run into good references. But I would say like also like reviews are a good source, but please go for the more recent ones, maybe not ones from 2025 itself, maybe from 2022 to 2024 period. These would be good references because, and you can also of course look at how many people have cited it and the like. So this is obvious, I don't want to state again. So but yeah, somebody has raised their hand.
So there is one more question. What platforms are suitable for trying out PQC methods?
So again, as I mentioned, PQC is not really like a quantum computing framework. So I would say that I'm not the best person to talk about that. But PQC, as I mentioned, again, it's classical. So you don't need any specific platform to work with it. You can run it on your laptop because it's purely classical.
All right. So thank you very much for accepting our invitation, for being a speaker on this FDP, and also answering questions of our participants. Hope people have enjoyed the valuable knowledge which you have given in last 2 hours with all the practical demonstrations. So thank you very much. We are ending this session.
Thank you.